Now we discussed rolling on a plane surface. Now I am going to discuss rolling on a inclined plane. Suppose we have an inclined plane, say something like this. Suppose this is an inclined plane and this is a solid sphere. This is a solid sphere. Suppose this solid sphere of radius r and mass m, suppose it is rolling on an inclined plane. Suppose it is rolling on an inclined plane. I have given you that the solid sphere of radius r rolls on an inclined plane. Suppose inclined plane, right, the angle of inclination is theta, and suppose we have to find the acceleration of the sphere and also find the minimum coefficient of static friction to support rolling. Okay, so here we are given the sphere is rolling on inclined plane. The sphere rolls on inclined plane and we have to find out the acceleration and the minimum coefficient of static friction required to support rolling. Now here the force which I can apply over here is, the forces are, one is your gravitational force. This is the gravitational force which will act, and since the motion of this sphere is constrained into the inclined plane, so there will be a normal reaction also. There will be a normal reaction. So this is the normal reaction. So you can see that these forces do not create any torque. So what do you say about friction? Will the friction act? See, we are given the information that sphere of radius r is rolling. On an inclined plane. Sphere of radius r rolls on the inclined plane. It means VCM must be equal to omega r. So you have some VCM, you have omega. We have VCM, this is VCM, and you have omega. So VCM must be equal to omega r. If the sphere is rolling, then VCM must be equal to omega r. See, VCM equal to omega r does not mean that VCM and omega both are constant. It doesn't mean that. They can remain constant, like we saw in case of rolling on a plane surface. The VCM was equal to omega r after the body starts rolling, and VCM and omega both are constant. We got the answer. In the last case, see, this was our case. So this one, we got this velocity. This was our VCM, and then we got the omega r also. This was omega. So in this case, your VCM and omega r both are equal and they are constant. Here, so they may be constant, or this condition can hold if VCM and omega r both are increasing, but they are increasing at the same rate. Then also it can hold. Means either you have VCM equal to omega r, VCM equal to omega r does not mean that VCM and omega r needs to be constant. It can hold till the rate of change of VCM is equal to the rate of change of omega r. That is, acceleration in the center of mass is r d omega by dt, that is alpha. If VCM and omega increase at the rate such that ACM equal to r alpha, alpha denotes the rate of increase in omega, ACM denotes rate of, or I can say alpha denotes rate of change in omega, and ACM denotes rate of change in VCM. So if this is holding good, then VC and omega r will remain equal. For the condition this must hold. You can have VCM equal to omega r if VC and omega r both are constant. In that case, ACM and alpha both will be 0. You can have VCM equal to omega r if ACM is positive and R alpha is also positive and they are equal. Means VCM increasing at the rate of ACM and omega r is also increasing at the same rate. This can happen when VC and omega r both are increasing at the same rate. This can also hold if VC and omega r both are decreasing at the same rate. So the thing is that VCM should be omega r. That will mean either VC and omega are constant, or they are increasing at the same rate, or they are decreasing at the same rate. So this is the condition which is required, so that VC and omega r increases, decreases, or remain constant. If it increases, they increase at the same rate. These are the rates of increasing VC and omega r. And if VC is falling, this will be the rate at which it will be falling. So they have to be equal. They have to be equal. Now see here. Here in the last case, like in the motion of rolling on a plane surface, we saw that when the body starts rolling, there is no tendency of slipping at the point of contact. You can see that when it started rolling at the point of contact, there is neither a tendency of relative motion nor actual relative motion. So friction does not act. But here the case is different. Here, see this mg. Mg has got a component. Mg has got a component in the direction of or along the inclined plane. See, this is theta. So mg will have a component that will be mg sin theta. Mg will have a component mg sin theta. And this mg sin theta won't affect omega, but it will increase VCM. This mg sin, this n is not going to affect VC or omega, but mg sin theta, mg has got a component along VCM. This mg sin theta is going to increase VCM, means it is going to create ACM without creating alpha. In that case, this mg sin theta brings a tendency of forward slipping at the point of contact. The moment you release the system, a tendency of forward slipping gets created due to mg sin theta. And the moment tendency of forward slipping is created, immediately the static friction starts acting in that direction. Say F is the static friction. You suppose F is the static friction. This is the static friction. The moment system is released, mg sin theta creates a tendency of relative motion, and the moment tendency of relative motion is created at the point of contact, the static friction does not wait for relative motion. The moment the tendency of relative motion arises at the point of contact, immediately the friction force starts acting, right? And this friction force will play a key role. See, what is objective of friction? The objective of friction is to oppose the tendency of relative motion, and it will be successful in achieving this objective if the point of contact remains at rest. And how can it remain at rest? If VCM equal to omega r and if ACM equal to R alpha. So F is going to act in such a manner, in such a direction and such a magnitude that VCM and omega r is going to increase at the same rate. F will act in such a direction and such a magnitude that VCM and omega r will increase at the same rate. See, in absence of friction, mg sin theta would have increased VCM without affecting omega, and the rolling would not have been possible. In that case, there would have occurred a forward slipping. So rolling cannot be sustained on a frictionless inclined plane. Like there in earlier case, rolling on a plane surface, rolling can be sustained on a frictionless surface also. Friction is required to begin rolling, but once the body starts rolling, friction has no role. Friction is not required to sustain rolling. There on a plane surface, friction is required to begin a rolling, but friction is not required to sustain a rolling. But here, even the body starts rolling, friction is required to sustain rolling. Without friction, the body cannot roll for a moment also, right? If there is no friction, if it is frictionless, the body cannot roll, because this condition cannot be satisfied, because mg sin theta is going to increase VCM without affecting omega r. So now see how F achieves its objective, how the friction force achieves its objective by self-adjusting its value to desired magnitude. See, the equation will be, if I draw this say x and y axis, say this is your y axis and say this is x axis, right? This is x axis, x and y. There is no motion in y direction, so n minus mg cos theta is 0, right? And net force in x direction is mg sin theta minus F equal to ma. And this friction force is going to create a torque also, that is I alpha 2 by 5 mr square alpha. So what do you find? You find that, see, in absence of friction force, your ACM would have been g sin theta and alpha would have been 0, right? If there is no friction, alpha would have been 0 and A would have been g sin theta, ACM. In that case, VCM would have increased at the rate of g sin theta meter per second, and omega would have remained constant. Omega would have remained constant. But see the friction. What friction is doing? Friction is decreasing this ACM and it leads to increase in omega alpha. It decreases its ACM. In absence of it, it could have been g sin theta. So it will lead to decrease in ACM and it produces alpha r, and friction act in such a magnitude and such a direction that they come to equal value. Alpha r and ACM will become equal, and when they become equal, VC and omega r are going to rise at the same rate. In that case, rolling can be sustained. So now we have to calculate what amount of friction is required to sustain a rolling. So if I write F, this will be 2 by 5 mr alpha, and F should act in such a magnitude that R alpha should become equal to A. That is MA. This is 1, this is 2. So you add 1 and 2, what do you get? You get this and this. So this is mg sin theta equals to sin by 5, that is 5 by 7 g sin theta. That's going to be the acceleration. That's going to be the acceleration. And friction required to sustain rolling. Sustain rolling is F equals to 2 by 5 MA, that is 5 by 7 g sin theta, that is 2 by 7 mg sin theta. This is the friction required to sustain rolling. In order to sustain rolling, this is the friction required. This is the friction required. And what they are asking you, they are asking you what is the minimum coefficient of static friction required to support rolling. So I must write required over here. Required to support rolling. So this is the friction required to support rolling. But then this friction value must lie within the range in which the friction can vary itself. Like, what I mean to say is, this F must be less than or equal to mu s n. Mu s n is the maximum friction which surface can apply, which interface can apply. And this friction required must be less than this value. Otherwise, if this friction required is more than mu s n, the surface will raise its hand. It will say, I can't sustain rolling. So in order to sustain rolling, The friction required must lie within the capacity of the interface. Interface can at max afford this friction, which is mu s mg cos theta. N is mg cos theta from here. So N is mg cos theta. So your friction required must be within its capacity. Mg cos theta. Sorry, less than equal to. So it means your mu s must be greater than 2 by 7 tan theta. Mu s must be greater than 2 by 7 tan theta. Right? This is the minimum coefficient of static friction required. Is equal to two by 7 tan theta. So this is the minimum value of coefficient of static friction required to sustain rolling. This is the mu s min. See, for a plane surface, the minimum coefficient of static friction required is theta. For plane surface, theta is 0. So minimum static friction mean coefficient of static friction required is 0. It means you can sustain rolling on a frictionless surface also. And on the extreme, if suppose it is a wall, what's the friction required? Coefficient of static friction required to sustain rolling? It is equal to infinity, which is not possible. So it is not possible to sustain rolling on a vertical wall, right? It's not possible to sustain rolling on the vertical wall. This is how we can understand this. Okay, so let's move to next question.